Review on modeling aspect of Ryanodine Receptor in CA1 Neuron. Abstract, Alzheimer is a neurodegenerative disease, which is most prevalent in worldwide. But there is no cure for it so far. From many reasons, elevated calcium concentration is one, that has their roles in this disease, and it starts at early stages. According to studies, Ryanodine receptor, RYR, can be targeted for further studies, for early detection of Alzheimer's disease, AD, and for therapeutic drug for treatment, since alteration in intracellular calcium concentration caused by many channel, among them one of is increase in expression of RYR, which increases the calcium flux at intracellular level. Also based on calcium-induced calcium release, it activates its neighboring RYR as well. So there is upregulation in intracellular calcium concentration, which deteriorate memory process. In addition, it affects action potential, shape, by the activation of large conductance channel, since it plays vital role in neurotransmitter release. In later stage apoptosis takes place, neuron cell death, which characterized by increase in memory loss, so neural connection decreases. Further, this Alzheimer starts in hippocampus, where there significantly reduction of neuronal density, especially in CA1 neurons. This occurs at an early stage of disease. In this paper we have explored the Ryanodine and their mechanism in neuron. Keywords: Alzheimer, neurodegenerative disease, calcium, Ryanodine receptor, calcium-induced calcium release. Introduction. Hippocampus plays a vital role in memory formation. Generally, cornuaminese, hippocampus proper, and dentate gyrus are the two parts of hippocampus. But, by some of the anatomists, hippocampus has divided into hippocampus proper, cornuaminese, dentate gyrus, subiculum, and entorhinal cortex, EC, area. Hippocampus proper, cornuaminese, is further divided into CA1, CA2, CA3, and CA4 based on histology. In that, CA1 plays critical role in contextual and autobiographical memory retrieval, re-experiencing detailed episodic memories. It also responsible for long-term potentiation, LTP. CA1 contains pyramidal cell, which is named due to its shape. It mediate cognitive functions. So, CA1 is the region, plays role in new memory formation and strengthens the memory 1, 2, 3. A. Alzheimer's disease. Alzheimer's disease, AD, which is neurodegenerative, results in memory impairment and affecting mainly elderly people. This happens because neurons, which is responsible for cognitive function, gets damaged, so, it diminish cognition, memory, language, and is defined by presence of dementia 4. The hallmark of the disease is defined by the presence of extracellular amyloid SS, AS, plaques and intracellular neurofibrillary tangles, NFTs, containing hyperphosphorylated tau, which in normal holds the microtubule protein together, acts as road for the transport of intracellular nutrient. However, in AD transportation of nutrients is blocked by NFT, and cell death occurs. 5. Hippocampus linked with memory formation, so the first degenerative process starts in hippocampus. Under AD, hippocampus begins shrinking, atrophy. 6. Then degeneration proliferate all over the temporal associated cortex, parietal areas. As AD grows, frontal cortex gets affected. It cause profound damage on various component of limbic system 7,8. In AD, there is significant reduction in neuron at CA1, CA3 hippocampal area. However, as per the analysis, there is huge loss in CA1 neuron density, in comparison with other level 9. At cellular level, calcium ion being a second messenger, plays vital role in physiological functions 10, in brain. These are neurotransmitter release, action potential, memory formation 11. So, fluctuation in calcium concentration beyond the required level, results in pathogenesis i.e. neurodegenerative disease, Alzheimer's disease 12, also perturbance in calcium concentration, occurs in advance of neuron cell death and cognitive decline in Alzheimer 13. Further, in Alzheimer, Ryanodine Receptor, RYR, expression at intracellular level, rises with early cognitive decline and neurofibrillary pathology, and at late stage, it reduced in CA1-CA4, subiculum regions 14. The calcium inside the cell is maintained and regulated by some channels located on plasma membrane, endoplasmic reticulum, and mitochondria. Here, in neuron, rise in calcium level results in neurotransmitter release at synaptic cleft, that contributes towards synaptic plasticity as well as action potential 15,16. Endoplasmic calcium at dendrites plays roles in postsynaptic process and synaptic plasticity 17 and at axon in neurotransmitter release 18. Calcium concentration is maintained at different level like 2 mm in extracellular space, cytosolic is 100 nm 19. Variation in intracellular calcium concentration underlies cellular mechanism of learning and memory, synaptic plasticity, include long-term potentiation, LTP, and long-term depression, LTD. High calcium concentration spike triggers LTP, in that during certain phase of sleep, information consolidate to permanent memory from temporary memory. Small rise in calcium activate long-term depression, LTD, during another phase of sleep, that erases temporary memory. While in AD, permanent rise in calcium erases temporary memory, before it can be transferred to permanent memory 20. So, change in the level of intracellular calcium get involved in brain activity, including learning and memory loss precedes the massive cell loss 21. 2. Literature survey. In Fig.1a, in response of neurotransmitter releases from presynaptic axon terminal, influx of calcium takes place from voltage-gated calcium channel, VGCC, at postsynaptic terminal, during depolarization 22,23. Then calcium interact with RYR, caused it to get open, efflux of calcium from endoplasmic reticulum takes through this channel 24. The second major intracellular calcium channel is ioncetal triphosphate, IP3, is ligand-gated IP3 channel. External stimuli acts on G protein, which activates phospholipase C, and generate IP3, IP3 diffuse from plasma membrane to endoplasmic reticulum, binds to and opens ligand-gated ion channel, calcium moves out from the endoplasmic reticulum into the cytosol, which stores calcium, and it activates various cellular function. However, mitochondria takes up the calcium using mitochondria calcium uniporter, MCU. Sodium/calcium exchange, NCX, moves the calcium out of cytoplasm 25. There is other calcium influx pathway, SOCC, store-operated calcium channel, which activated when ER calcium depleted. In that stem which sits in the ER membrane, forms clusters, closure to the plasma membrane, interacts with ORA, forms a calcium channel to allow calcium influx from extracellular medium. Also, depleted ER calcium store, refilled by sarco/endoplasmic reticulum AT posse pump, CIRCSA, pump 25. Fig.1a, intracellular mechanism in normal neuron. Then increase in level of intracellular calcium during action potential depolarization led to activation of calcium-activated potassium channel, situated near VGCC 26. Ultimately, efflux of potassium ion and closure of calcium channel takes place and it produce after fast hyperpolarization 27. So, it contributes in maintenance of shape and duration of action potential 28. Fig.1, b. Intracellular mechanism in Alzheimer. It is important to have proper balance in calcium hemostasis, for neuronal survival and memory formation, synaptic plasticity. However, in AD, in Figure 1, b, there is increase in VGCC, by which calcium influx rises 29. Ryanodine also works with increase in its expression 30-31-32. Presenilin acts as leak channel 33 and it also alters the normal function of CIRCSA 34. Also, gating of IP3 increases, due to interaction of presenilin with IP3 receptor 35 and stimulation of mGluR receptor linked with IP3 production 36. In addition, depletion of endoplasmic reticulum calcium activates store-operated calcium entry via the stim/ORAI pathway 37. An efflux of accumulated intracellular calcium level via sodium/calcium exchange, NCX, gets inhibited in Alzheimer condition 38. Increase calcium cause excessive flux into the mitochondria that increases its overload, generation of superoxide radicals, caspases, and cytochrome C, that led to cell death, apoptosis, 34. In addition, raised intracellular calcium level affects LTP34 and action hyperpolarization, which are result of calcium-activated potassium channel 39. Also, increased calcium level, increased activity of calpain, which in turn led to tau hyperphosphorylation 40. So all might ultimately contributes towards later stages of disease, that is cell loss. So under AD, malfunctioning of these channel, results in increased intracellular calcium level and it has deleterious effects on the functioning of cell membrane permeability to potassium ion, which is vital for neurotransmitter release and many other cellular function is controlled by intracellular calcium 41. In hippocampal pyramidal neuron, ryanodine receptor are present at higher level, which is activated through calcium influx from VGCC, followed by calcium-induced calcium release, CICR, which dominate in CA1 neuron for ryanodine receptor 42, so there is link between AHP and calcium release from ryanodine receptor. Also, ryanodine receptor on stimulation, enhance memory process 43 and on blockade RYR, in mouse model it reduce memory impairment 44, however, it induce amnesia 45. 3. Mathematical formulation and analysis. Here, the author has conduct research on RYR in cardiac myocytes, to find RYR adaptation. With increase in calcium concentration, open probability of ryanodine channel increases. Fig 2 transition among 4 state of RYR. Step A and B is only calcium dependent 46. In figure 2 C1 and C2 are 2 closed state, whereas O1 and O2 are open state. At low calcium concentration it is C1 states. In transition state, state C1 to O1 and O1 to O2 are calcium dependent, which depends on binding of N and M calcium ion respectively. The step in the absence of O1 to C2 are considered to be CICR. On slow transition from O1 to C2 it exhibits inactivation. When we translate the schematic diagram into kinetic equation using mass action law, then differential equation can be written as follows. NDPC12 plus. We can deduce that how this vary with time. The equation for peak open probability is given by 46. Peak, CA2 plus, equals, WINF, 0.1 m, plus, CA2 plus, slash KB, caret 3, slash. 2 plus 2 plus. 1 plus, ca slash CA, caret 4 plus, CA slash KB, caret 3, 5. Where WINF, 0.1 m, is the equilibrium value of 1 PC2 evaluated at the initial value CA caret 2 plus equals 0.1 m. Plateau value of PO is equilibrium value of PO1 plus PO2 and it can also be written as POPEN. So, open probability, POPEN, of ryanodine receptor, normal, from Kaiser and Levine is given by 46. 343. C. Casey. POPEN equals W, 1 plus, slash, 1 plus, plus, 6. KB C KB. Where W equals 1 C2, fraction of channel not in state C2, Ka and KB are kinetic parameter. W determine the rate of relaxation to its plateau 47. JRYR equals VRYR times POPEN times, SC, 7, the driving force for the flux is endoplasmic reticulum membrane calcium gradient is, SC, 47 herein, AD, open probability of ryanodine receptor increases. In the absence of external calcium fluxes, closed cell model, the mechanism led to BIST ability. Kinetic model of ryanodine receptor is used to describe CICR from internal store. This is combined with a passive leak and CIRCSA pump that returns calcium to the store. 46. dCdt equals V1 Popen plus V2 S C V3 asterisk C2 plus K32 8. Table 1 simulation parameter. Property value reference. Kinetic parameter Ka 0.372 M47. Kinetic parameter KB 0.636 M47. Kc kinetic parameter 0.057147. VRYR 10,6 / 47. C. Calcium concentration in cytosol, 0.1 to 0.9 M46. S. Calcium concentration in ER250 M49. Table 2 parameters for closed cell. Parameter value meaning reference. V1 40s to 1 rate constant for RYR, 47. V2 0.5 S1 rate constant for store leak, 47. V3 1000 ms1 maximal rate of CIRCSA pump, 47. K3 0.30 m dissociation constant for CIRCSA, 47. Fig 3a is Po equals Po1 plus Po2, where calcium vary from 0.1 to 0.9 m. Activation takes place in milliseconds while decline to plateau in seconds. In figure 3b is inactivation is there, with time scale in seconds. Fig 3c, here first variation in calcium ions occurs from 0.1 to 0.35 at t equals 0 followed by enhancement up to 0.50 m. Fig 3d the peak and plateau that depends on calcium, solid curves is theoretical value. Like that in Fig 3a where, as is experimental data, upward facing triangle is peak and downward is plateau. 46. Another RYR model with no time dependence or gating kinetics was constructed by Friel, 1995. This calcium model is based on calcium oscillation in sympathetic neurons. 48. Here, flux is proportional to concentration difference. JRYR equals K3, CE, C. Where CE and CRE are calcium concentration and cytoplasmic calcium concentration respectively. And where n equals 3, the first factor K3 is open probability, where K1, K2 and Kd are parameters. The parameter K1 is the zero calcium concentration level leak. Kd corresponds to RYR channel sensitivity for calcium-induced calcium release, CICR, and K2 is the maximal rate of channel. 48. 4. Conclusion and future scope. This review paper attempts to explain what generally happens at intracellular calcium signaling in Alzheimer. In AD, there is upregulation in calcium at intracellular level by internal stores and extracellular mechanism. Among them, this review focused on ryanodine receptor, in which there is increase in expression of ryanodine receptor, that is open probability of RYR increases. In addition, RYR involves in memory process, and calcium released via this channel takes part in action potential. So, in future, model will be focus on RYR open probability and from them we can drive flux and current.